Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll begin a new unit called Current Electricity. Up till now, we've been dealing with electrostatics, in which the charges were static. The charges were never moving from one point to another. We saw the electric field due to charges, we saw the potentials created due to charges, but we never moved the charges from one point to another, except when we moved one particular charge very slowly to define the potential difference. Now we'll deal with the second aspect of electromagnetism, which is called electrodynamics. Now, electrodynamics also involves charges which are moving from one place to another. And whenever a charge, let's say a charge Q, moves from one place to another from point A to point B, we say that a current has flown from A to B. If the charge Q is negative, then we would say that the current has flown from B to A. So let's look at a numerical definition of current. If we have a certain amount of charge flowing through a certain area, let's say this is the area delta S, then flowing in a time delta t, let's say delta Q amount of charge is flowing through a delta S area in a time delta t, then the average current is defined as delta Q by delta t. The current through an area is defined as the charge crossing through the area per unit time, right? So the average current will be the total charge that has passed through a certain amount of time divided by the time interval. If we wanted to calculate instantaneous current, you probably know how it goes. Similar to kinematics, it will be dq by dt, right? So if we are told that q is equal to 3tq plus 2, that means through a point charge is flowing such that q at any time at that point is 3tq plus 2, then the current flowing out of that point will be dq by dt, that will be 90 square. Another quantity of importance is the current density. Current is represented by I, current density is represented by J, and it is a vector whose direction is same as that of I. So the current density is a vector whose direction is the direction of the flow of current and whose magnitude is defined as I divided by delta S perpendicular. Now what is delta S perpendicular? It is the component of area perpendicular to the current. So let's say the current is flowing in this direction and this delta S is the area. We've seen a similar thing in Gauss law when we were talking about solid angles and flux. So the area we will actually have to take will be this, and if this angle is theta between them, that is the angle between these two lines is theta, the perpendiculars to the areas, then delta S cos theta will be this perpendicular area, delta S perpendicular, right? So we can write mod J as I divided by delta S cos theta, where theta is the angle between the area vector and the current density vector. We can take delta S cos theta to the other side, and since we already know that the direction is the same as that of the current, we can write I is equal to J dot delta S. So J is current per unit area, so current has to be current per unit area multiplied by area obviously, but we see that it's actually a dot product because the current density and area both are vectors. This is for a small amount of area, it probably would be di is equal to J dot ds. For an extended area, the equation would be total current is equal to integral over that area J dot ds. So we've seen two new quantities now. current and current density. The important thing to remember is that the area, when you're talking about current density, has to be perpendicular to the current, or the area has to have the direction vector along the direction vector of the current. Now what we'll try to do is we'll try to relate the current to the electric field which we apply across a conductor. So let's say we have a conductor. It doesn't need to be cylindrical, I'm just taking it for the sake of simplicity, and we apply an electric field in this direction. That could be applied by keeping a positive charge sheet here. It could be applied by attaching these two ends to a battery, which would create a potential difference. There could be many other ways of applying an electric field. So when we apply an electric field, charges flow from one point to another, and that results in a current flowing across the conductor. And our goal now is to calculate the relationship between the electric field and the current flowing through the conductor, right? And that will end up being what you've already seen in earlier previous classes in 9th and 10th as your familiar Ohm's law. So we'll start by taking the most basic method, which is we'll calculate the motion of an electron. So let's say we have one electron. Let's say this is the material and we have one electron. Now electrons typically are very small, so then they don't generally collide with another electron except after time intervals. They don't always keep colliding. So the general path of an electron within a conductor would be something like this. They could also actually much more likely hit a neutron or a proton, right? So this is something like what the path of the electron would be. It goes in a straight line until it hits something. Once it hits something, it goes another place until it hits something else. Once it hits something, it goes another place. This is the same behavior which we modeled when we were talking about kinetic theory of gases, right? So all in all, if there was no electric field, then the net movement of the electron would be zero. The total lines towards the right would equal total lines towards the left. The amount it moved towards the right in a certain time would equal the amount it moved towards the left on average, and it would not have any particular movement. But if we apply an electric field to the right side, right, now one problem we generally have here is that, and this problem actually goes back historically, because when Benjamin Franklin discovered electricity, he saw two charges and he could have named either one of them as positive or negative. As it happened, the one he named negative was the one we later found out to be the freely moving charge. So that makes things a little bit confusing, because whenever electrons have an electric field applied towards the right, they will move towards the left, but the current will be towards the right. Right, had there was a 50-50 shot, had Benjamin charges called the electrons the positive charge, then this problem would not have arisen, right? But anyway, we're stuck with it. So if in a random case the electron moves like this, once you apply an electric field, it will keep shifting towards the left a little bit. So instead of going here, it will probably go something like this. Maybe it will hit something else, it will go like this. Maybe it will go like this, it will go like this. The point is, the whole average motion of an electron would be shifted towards the left because of the electric field, and we would have what is called a drift of the electrons. That does not mean any electron would go from this end to this end, but each electron's movement would be shifted slightly towards the left between each successive collisions. So how much would it shift towards the left? We can calculate that easily. If tau is the average collision time, or the average time between collisions, in that case, between any successive collisions, it would have an acceleration towards the left of e by m, because e would be the force divided by m, that would be the acceleration. So if the time between this collision and this collision is tau, we are assuming tau is the average time, then between these two times it would have moved towards the left a distance equal to half at square, right? Let's call this L vector. L vector is not this vector. This vector is the standard motion. L vector is the amount deviated from this due to the electric field. Of course, the average velocity towards the left in that case would be L by tau. That is called Vd, or the drift velocity, and that will be equal to half e by m tau, right? So this is a very important formula you need to know, and it tells us the speed with which electrons move through a conductor. Now this is actually a very interesting thing, because drift speed is not the speed with which electrons move towards the left. Electrons are moving there, or just moving within their region, colliding with other electrons, and the whole system is moved slightly towards the left between any two collisions. So Vd is actually the speed with which effectively the charge flows from left to right. And actually, whenever wire is flowing, current is flowing through wire, Vd is generally of the order of centimeters per second. So it is quite a different quantity from what you have seen. You would expect speeds of electrons to be quite high, and they are quite high. But because there are so many electrons, and the charge is so small, E, that the electric field only slightly affects them towards the left, they keep slightly moving towards the left, and it feels as though charge is moving from the right towards the left. Whenever you have a circuit and current is flowing, let's say here is a battery, resistor, capacitor and stuff. When charges flow from this point to this point, no single electron flows from this point to this point. The electrons are there, they just shift slightly towards the left, which causes the electrons left of them to shift slightly towards the left again. And that process creates current flowing, and that speed is generally of the order of centimeters per second. Right. So this quantity is called drift speed. It can also be written as half E tau by m electric field, which is written as mu electric field. This is basically the definition of mu, which is called mobility. So mobility is the measure of the speed of the electrons with respect to the electric field applied. But this speed, remember, is the drift speed. So now half our work is done. We've related the electric field to the drift speed. We wanted to relate the electric field to the current, so now we'll have to relate the drift speed to the current. Right, so let's see that. Imagine if we have a conducting material. Let's say the area of cross section here is A, and electrons are moving with a drift speed of Vd towards the right. Right, let's call this length L, which is equal to Vd times delta t, which is the length which the charge would move in a time delta t. Right. So during this delta t time, charge is flowing through this surface. Let's say charge is going in this direction, then the charge flowing through this surface in delta t time would be the charge within this whole material, because if it's flowing with the speed v, after delta t time, this point would be here. So the total amount of charge flowing through this surface would be the charge of one electron multiplied by the number of electrons flowing through this surface. All the electrons within this material will cross this surface after time delta t, because after time delta t, this end would be here and this end would be here. Right, it would have moved a distance of delta t. So E multiplied by the total number of particles within this volume. What is that? That will be N. N is a standard quantity for materials, which is the number of particles per unit volume, the particle density. Right, multiplied by the volume of this region. The volume of this region would be A Vd delta t. Right, this is delta Q. It should probably be written as delta Q, the charge flowing. From that we can get delta Q by delta t, and we can divide it by further A to get the current density. So we'll get the result, the current density J is equal to NeVd. The number of electrons per unit volume, or the number of charged particles per unit volume, multiplied by the charge on one particle, multiplied by the drift speed. Right. So now we've related current, or rather current density, to the drift velocity. Now if we put the value of Vd from the previous question, what we'll be left with is J is equal to Ne times Vd. Vd will be E tau by 2m capital E, which will give me Ne square tau by 2m capital E. Wait, this is tau. So let me just clear this page and write this properly. The result we got was J is equal to Ne square tau by 2m E. And that is the result. This is the familiar result, Ohm's law. Possibly this might not look like the Ohm's law which you know, but for that you just need to wait a second. For now you need to realize that we've completed our goal. We needed to relate the current or the current density flowing through a wire when we apply an electric field E in the wire, and we've done that. Now if we take, let's say, standard material. By the way, this particular quantity, Ne square tau by 2m, is referred to as sigma, or the conductivity. Right, so the actual Ohm's law is J is equal to sigma E. Right, but if this area is A, this length is L, a current J is flowing through this direction and an electric field E is here. Right, then we can actually write it in a different way as well. J can be written as the total current flowing, I, divided by the area. That is equal to sigma times the electric field. The electric field can be written as, if these 2 points have a potential difference of V, then the electric field will be V by L. Right, so electric field can be written as V by L. From that we get the relation V is equal to I into L by A into 1 by sigma. 1 by sigma we can write as rho. Rho is equal to 1 by sigma, and rho is called the resistivity. I'm sure this stuff you've seen in earlier classes. So what we get is V is equal to I times rho L by A, and rho L by A is called the resistance. So from this Ohm's law we get the more familiar Ohm's law, V is equal to IR. Right? I think that should be enough for this video. In the next video we'll move forward in this topic. Okay, one small thing I'll say more in this video. Resistivity is related to the material. Right? If you give me aluminium, I'll tell you the resistivity of aluminium. Resistance is resistivity along with the length, along with the area. So resistance has to do with the material as well as the geometry of the object. So a 5 mm thin wire of aluminium will have a different resistance from a 2 mm thin wire of aluminium, because A would be different, though they would have the same resistivity. Also, similar to, just like you have resistance and resistivity, you have conductivity and you have conductance. Conductance is 1 by resistance, and it's generally not used, but it's nice if you know it. Right, so conductivity, resistivity, property of material; conductance and resistance, property of the actual object. Thank you.